um, uh, right? So I'm going to take A, B, Now, why am I doing recursive? I'm doing recursive because I essentially want to do the following recursion tree. I have a root where I haven't picked any of these things yet, then I'm going to have to descend one stage for each stage of that list. So there's going to be like the thing where I'm looking at A, and then I'm going to be looking at C, and then I'm going to be looking at D, and then there's the thing where I'm looking at B, and then I'm looking at C, and I'm looking at D, right? So at each layer of the recursion, the first layer is, you know, this call, and then each after that it goes like, look at this list, look at that list. It begins an iteration over a list that I pass down to it. As it iterates each step of that list, it will once again call the recursive function on the next list after that. If there isn't a next list, then instead what it'll do at each step of the loop is try to emit that combo, so A, C, A, D, B, C, B, D. So if I actually want to do that, in addition to everything I've done so far, I'm going to need to be able to pass down sort of a growing I guess like field pin list. Is it a pin list? So just to be clear, this thing here is the full set. This is a pin list. And that's right. I need to be able to get the list that has the A and the C on it. So it'll be like that, right? Yeah. And so that initially, the growing list needs to get passed down there with nothing in it at first. And then that'll grow as we recurse. Okay, so how do I do this? We do a loop. Well, let me see the field pin list type. I do a loop. That's a better way to do it. Field pin. I look at everything in the list I've just been given. For each pin, what I do is I say, okay, make a new like copy of that pin that's like local pin equals pin. Push that onto the growing list. So I have this thing here, it's initially 0, 0. It's not going to point at this guy here, who's got the same information as him, but his next pointer is going to be looking different. Right? And then we obviously need to do this. Probably do that right here. Undo it right here. And then, actually we don't need to undo it because they have separate copies. And then call the recursion again on the next list, growing list result, right? The next list, we can get that by just doing that. And then finally, if we in fact do have no next list, so someone passes a next list pointer that was null because they were the last of the lists, then I have the job, instead of emitting, or at least checking if I should emit and then only emitting if I should, a new list into the result. So what I do is I say has conflict equals false for every node in A, where a node is a field pin, and for every node in the thing we're going to attach to it, so I'm calling it B pin. If the pin's flag equals the B pin's flag, so they're both pointing at the same flag, and the pin's value is equal to the B pin's value, then the problem with that is that when we flip the B pin value, which is what we do to get its complement, they would be incompatible. They couldn't exist together. And then we say has conflict becomes true. Now, maybe we don't want to do it like that. Maybe what we want to do is say, look, we're going to have a restore point on the arena, right? And if we get there, I mean, we'll still maybe need to say has conflict or something, but we also just want to get rid of all the memory. Not sure why I'm getting... Does this not have any other begin temps? That's crazy. Has conflicts equals false, and then this can break. So if it finds a conflict, it'll stop. But why is it even doing a restore point? I'm not allocating anything. What does the restore point do? The restore point will do something. What it's going to do is, as I'm going, I'm creating a new list of pins, and the rule is actually, I don't think that would work. I mean, it just wouldn't work as a nested loop. So forget that. Oops. We do need that, we do need that. So if it does not have any conflicts, then what we do is we say, great, no conflicts, we actually are going to emit this thing. We need a new list. And then we need to iterate all of the nodes in A, right? And I'm just doing that so that I can avoid having to type that nonsense out twice. New pin, sticking onto the new list. There it is. Then I'm going to do the same thing I did here, only I'm going to be doing this exact thing again, and I'll just go ahead and call these pins instead of B pins now. But there is one difference, which is before I can do that, I have to do this again. But I'm looping over A pins, and I'm getting my pins from the new list, right? And the point is, if at any point I find that these are the same flag, then they are redundant and we don't need that flag to be pinned twice. And this is the part that I thought, if I was clever, I would avoid up here, but just, I don't know. Maybe I actually could. For each of those, we're going to copy A exactly. If the flags are the same, this will need to be a double break. If the values are the same, we have a bigger problem. It has conflicts. Otherwise, just regular break. And the restore point, come on, restore point, there we go. So if we start here, and call this restore point, we start building this new list, so we allocate that, we copy in all the pins from the source thing here, and then we what am I doing? I see. Right, and obviously what I should have done was this. Everything but that. Again, everything but that. There, that copies that into there, and that into there, and then it builds one of those. Okay, so then this here can actually just say that screw all this. New list is going to start off life as a copy of A, and then we're going to iterate the things in the B list or the growing list. For each of the things we find, we check to see if it's a duplicate or it has conflicts. If it's a duplicate, then we just skip it, but keep going. If it has conflicts, we break out of the whole doubly nested loop here, and we mark that had a conflict, and we say throw away the memory we've set aside for this thing so far. And then finally we say, man, I hate that feature. This is such an old version of 4coder, and it kind of slows me down, honestly. But the newest version of 4coder isn't stable, and I can't really get an intermediate very easily without putting in like 20 minutes of Git nonsense, and I don't like having to do that, so I'm just trying to put up with this. But it's annoying. I can't do things that I'm used to doing. Okay, so if we get to the end and we have not got any conflicts, then we can add this into result finally. Yes, so to recap how this whole thing is working, here I'm initializing a recursion. The recursion goes through a series of lists. At each step of the recursion, it iterates to the next step of the list. So recalling myself, every time I call the recursive step again, I go one step farther in the list, or rather, I go to the next list, right? Now, each list, I then loop over that list. So there's like a series of lists. At each stage, I call the next stage by calling it with the next list in the order, but then at that stage I loop over all the elements in that list. In this way I'm iterating every combination that I can get by selecting one thing from each list. And if I get to a point where I don't have a list anymore, someone called me but their next list was a null pointer, that instead what I do is I use the list that I built up here and I can get rid of this now, to try at least and construct a new list for the result. Now the way the new list gets constructed is I iterate the elements in the list that we've been building this whole time, the B list here. Well, first I copy the things that we know we're going to keep all of this list, and then we're going to try to keep as many of these things as we can. We don't keep anything that's on the same flag, and if it is on the same flag and it's got the same value, we have a problem where this whole list is actually not relevant. The whole thing just represents an empty set, because there's going to be conflicting pins. If they're not the same value, then when this gets flipped down here, we would end up with duplicate flags in the list. So either way, we don't emit duplicate flags. We just check to see if it's a conflict or a duplicate first. And then finally, we put those flags together, and if all of this finishes and we've successfully built a full list of new flag pins, we put it into the result. And then, this happens several times. This stuff does here. One for each list that has to go into the result. Set subtract. Yeah, let's take a look. Yikes. Copy the pin. That's the B pin. Arena. Okay. I'm ignoring that. Okay, so there we go. That's how we subtract field sets, I think. How do we intersect field sets? Well, intersecting field sets is actually the easy part. We've actually already done intersecting field sets, essentially. So when we were subtracting them, we had to do this whole thing. This is actually essentially implementing an intersection. Wait. What is this code? Well, this is the wrong stuff. This is the overcomplicated stuff. This is the less complicated version. This implements essentially an intersection, which is concatenating two things together, eliminating duplicates, and making sure that it's not empty. So we can do the same basic idea here again. So our field set, the only reason we can't directly do that is this is a field set. A list and a list are easy to intersect, but a set and a set are a little bit more complicated. Let's take a look at this more fully, actually. Separator, bloop. So there's going to be, we have an intersection union another intersection, and we want to take all of that and intersect it with something with the exact same format. So this is the problem to study now. What does that turn out to be? Well, this is just a matter of distribution, like distributing things over each other. So let's say we're going to take all of the second set and intersect it directly into these. Intersect U, union, intersect U. So again, this is actually just a matter of breaking why don't these line up? Oh, I see. Yeah. Okay, so what this actually turns into is just we do the first part, like the first list and then the second list, right? We can apply a list, we can take the full set on the right-hand side and apply it to each list individually on the left-hand side. So let's study in particular how this affects one single list. So we still have the problem that there's this union here under this intersection here, but now we're going to spread that intersection out across across this union here. So it's going to become that and that, with the parentheses drawn in there and there. Of course, now we have just intersections and on top of them unions, which is what we wanted. And you can see this works out a lot more simply than the subtraction case. For this to happen, all I have to do is make a new list, which is the combination of this with the first list and then this with the second list, right? Basically, for every list in the second set and for every list in the first set, we're going to end up with one new list. Or to put this another way, here we have a list A, B, and a list C, D. Then we have another list A, B, and another list C, D. And we're going to intersect those two things together. What we're going to get is going to look like this in the end. C, D, C, A, B, right? Every list in this set and every list in this set get concatenated into a new list. That's all that happens. As before, if any of the things we look at are conflicting, although not when they're flipped, but before they're flipped, like as they are, if they're conflicting, those become empty sets. Anytime we have duplicates, those become redundant, and so some of that will shrink down. In fact, I expect most of the time we'll never get to like as many as what the math shows, because most of the time these will be like this, which would just become, or like this I mean, which would just become one single list, or it'll be like, right, because there'll be nothing else in the union and stuff. And then as it slightly gets more complicated, that will intersect with another thing. and become this. Then eventually someone will subtract that from that or something, and then it'll blow up a little bit, and we'll finally have unions in there, and it'll start getting complicated. But it's going to take a while for these things to actually grow out, and it doesn't in real world scenarios, I don't think, ever have to go more than a few steps of look ahead to find what it's looking for. I guess it's a little bit complicated when it has to subtract out, like when we're doing the eclipsing for fallbacks. That's the case where it could actually start to cost something. You know, start to look like this. But anyway, point is, this one's not as complicated. We can do this. So this is going to have a very similar structure to this at the top level. It's iterating the lists of A and doing a field pin intersect. And then the biggest difference is that field pin intersect, although also going to be recursive, is going to be recursive in a very different way. For each of these lists, wait, do I even need to do this? No, this is actually not necessary at all. No recursion. We're just going to do a doubly nested list of, yeah, this is better. Field pin list B list equals B dot first. These become the A list. So for everything in the A list, we take a look at everything in the B list. We copy the A list, so temp memory restore point, begin temp memory arena. We make a new list. Copy the A list, and then we say, same thing we set up here, essentially. There might be conflicts. We iterate the flags. Actually, that was a mistake. These are the A flags. Or I can just call them regular flags, I guess. These are the B flags. We have a copy of the A list, so we iterate the B list. We checked it for each thing. Are you a duplicate or a conflict? If it's not a duplicate, if it is a conflict, by the way, we just go to double break. If it's not a conflict but it is a duplicate, we don't do anything. If it's not a conflict or a duplicate, we copy the pin, the B pin, and we push it onto the new list. We don't alter its flags in this case. And then we double break. If we get this far and we do not have any conflicts, then we push the new list onto the output struct. Oops, that wasn't quite done. Okay. So that's how we do a field set intersect. Good. Field set union is actually the easiest of them all, because all it takes to union these is to concatenate the sets themselves. Or to put it another way, if we take a look at the definition here, right, I have each set is a list that is a union of its members, so the union of unions is just a union, and since this is a union, we can represent the union of unions is a union by making these two things come together. So, actually I'm not even going to go that far. What I'm going to do is if a dot first does not equal 0 and b dot first does not equal 0, then a dot last next equals b dot first. A dot last equals b dot last. I suppose I probably want to copy though. Field set result equals SMI field set copy. So we copy A, and then we're going to say, alright, if, I guess I don't even need to do that. What I'm going to do is I'm going to say if neither of them are 0, then we copy A, and do this stuff here. Ooh, that doesn't quite work either. Why don't we do it like this? Copy them both, and then set result.first equal to a.first, a.last next equal to b.first, result.last equal to b.last, and result.count equal to a.count plus b.count. Else, and I guess what I really want to do here is say, let's do the four-way. So if none of them equals 0, we copy them both and concat. If A does not equal 0 but B does, then we just make a copy of A. If A does equal 0 but B does not, then we just make a copy of B. And if both are 0, then we are returning 0, so we do nothing. Okay. How does that look? This is perfect. Okay, now we need to do these constructors. Field set. You are empty. You have all of the all field possibilities are available, so there are no pins. Therefore, there are no pin lists, which represents a full set, and therefore, it's a little confusing. So if you have an empty union, I would interpret that as an empty set. But if you have an empty intersection, I would interpret that as a full set. But if you have a union of intersections and it's all empty, what does that mean? I don't know. I'm going to just write the shorthand rule for this system that the empty field set, or the zeroed out field set, is the full set. Because that way I don't have to do any work to get the full set, which is the very, very common case. Okay, so field set construct with a single field there. It's going to go like this. There's a result. It needs a single field pin list. It needs a single field pin. It needs a flag and a value. right? Yeah, so there we go. So there's the entire set of things for field sets, which is nice to have. Then there's the entire set of things for input sets. These are simpler in terms of their algorithm descriptions, just complexity. Oh my god, twice? Copy, paste, there we go. Result.inputs, push array, arena u16 set count, result.count equals set.count, push array right, set.inputs done, set subtract. Result equals SMI inputs set copy, copy A, for each thing in A, well in result now, for each thing in B, if don't really like that name, but I couldn't think of a better one. If is subtracted, then what happens is result.inputs I equals result.inputs result.count minus 1. Although actually we're going to rewrite this to do the minus 1 right there. And then the I minus 1 right there. So anytime we subtract something out of the set, we blah that right there, right? I'll go ahead and add in a quick restore point the arena. And if it turns out, which it often will occasionally on a non-trivial occasion, on the non-trivial occasion, it will turn out that count is equal to 0. We'll just go ahead and trigger that restore point and then zero out the result. Right? And actually, I'll go a step further and say that all of this only happens if there's anything in A to begin with. Not that any of that would cause a huge problem, but the push array doesn't really like getting past a 0, so that would be the only problem. And I might as well just not do any of the extra work since I have to do the if anyway. Okay, so there we go. That's how we do a subtract. Super. And intersect is going to look extremely similar. Not shared. Okay. So this one is not as exactly a copy paste, but it's still not going to be like okay. So for this one, what we have to do is, we can't do this copy. What we actually have to do is a little different. Inputs equals push array onto the arena of U16's A.count plus B.count, since we don't know how many of those are possible, but that's the maximum it could be. Then what we're going to do is, for everything in A, which we can get by repurposing this loop here, for everything in A, well, we can do better than that. We can just block copy into result inputs everything that A already has. This is a dynamic array that we're block copying. That way the count knows what it's talking about. And then we do this one. And for this, what we do is just going to be kind of like this. Is duplicate result.inputs equals if result.count, if result inputs j equals b inputs I. So we loop over everything in B, then we loop over everything in the result that we're building up. If they are equal, then this is a duplicate. Then, if it is not a duplicate, we will stuff into there b.inputs I and increment the count by 1. And then if we get to the end and result has the 0 count, then something impossible happened. There we go. So that's how we union those. Then I need the constructors for these, which I've written a couple times already. So let's take a look at what I did for these. So ignoring all of that, the constructors on these are like this. Result.inputs, result.count, characters.size, that's how we construct one of these sets when it's off of an array. Here's how we construct one of these sets when it's just an end of file. And then to construct one of these sets when it's a fallback is the case where you grab that and you do a loop. And the loop goes to here, and it does something just like this. Okay, so there we go. We have all of that up and running. Now this thing here, yeah, I eliminated that. So input set, what are you? You're a member of condition node, and then we have a condition set, and then finally the case has a condition set. Okay, so who's calling case construct? I don't know, but it's not relevant anymore. We're going to build a new one. So down here again, and again, let's write this thing. And then we can call this done. It turned out to be a two episode streak that I went on here before I found a good stopping spot. So if I am trying to create a character array what I want is condition set that is constructed out of an input set on this arena with these characters, and a flag set a field set that is constructed on that, right? And so I need to go and change one thing about how my field set constructor works, which is that it doesn't check to make sure that flag is not 0 before it does this, which would be bad. So there we go. And then, yeah, I might just, I don't care. Set construct. There we go. Then, if I have both of those, making the thing that puts those together is just a matter of saying, look, transition, wait, I already have that written there, what am I doing? So a single solitary condition can be constructed as a condition set. If I have an arena, the input set, and the field set, I can go like this. There we go. Node on the inputs and fields, push it on there, push that on there, and there we go. How does that look? Fair enough. How does that look? Closer. So all of these are condition set cases. Condition set. Right. To do these other ones is just to copy that and change how I construct the input itself. Input set construct EOF. Goodbye. Construct fallback. Value. value, 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 value. Still recovering from that earlier near disaster thing, and there we go. So now I don't need this at all. Okay, so simplifying transitions would be nice, but I'm going to say that that is a goal for the future. I just want to get back to, there we go. And do we have... Uh-oh. Alright, so it's building, but it's also crashing. So I can't shut down the episode just yet. I still need to look into that. So these maybe be slightly longer episodes, but I hope that's okay. So this is, oh, this is just for 4ed. That's the wrong debugger. I don't guess I have one up for this. So you can't see this on OBS or on YouTube or in the video at all, but because OBS won't record it. But I'm popping it up in Visual Studio, and it's taking forever, which is sort of the way things go. And there we are. See if I can properly examine this. Okay, so it's right here during the construction of the model that something's going wrong. Slot count is 0. I thought I was protecting against this these days. Okay, well, who's doing that? Guess I wasn't. Okay, well, whatever. Not that big a deal. Okay. Okay. Let's see. I'm guessing. Yeah, okay. What else have you got? Alright, so I think that's as far as I'm going to get for now. This is hitting stuff that we haven't actually looked at yet. Although it might be worth it to just take a look at all of this, make sure everything can run so far. So it's been a lot of development time without having tested any of it yet. And just making sure it can at least run through and build the structure I think it can build would be a good move, probably. But let's see what's going on here. I'm asserting that I found a match. Why is that? It's because string to state, if prefix size is 1, right, prefix size is 2. That means, okay, so I'm on I equals 2, right? So, okay. I'm guessing this is just the first time this ever happens. Yeah. Okay, so let's actually walk through this real quick just to get an idea. Maybe I'll debug this next time before I do anything else. So I guess the first lexeme had a size of 1. Yeah. So anything with a size of 1 has no prefixes, and so naturally doesn't do this. Oh, by the way, I haven't explained what this does yet. We're trying to iterate through all of the prefixes of the operators. So here we go. Here's a prefix. I have the operator or the token I'm trying to add to the system is : : and so it has one prefix, which is : and so then we look that up into the table. We haven't added that to the table yet, so it becomes an intermediate state, and then we set its parent to root because it's a prefix with length of 1, so nothing was consumed before reaching this part, and there we go. Lexeme of size 2 again. Any lexeme of size 2 will never trigger this case, so I don't need to look at it. Lexeme size 2 again. Need to find a lexeme of size 3, and it might take a little while. So, size 1, size 1, size 1, size 1, size 1, size 1, aha, size 3. So the first one, we get a prefix of size 1. Look it up. We have not found a match because we haven't had anything that started with a dash that was longer than 1 yet. Parent. Oh, but that never gets inserted into the table. The table's not been growing this whole time, has it? I see. 1626. So, whenever we are looking at a prefix, if we didn't already have that prefix in there and we had to do all this, we also need to do the table insert for the prefix. So insert into the string to state table, make the data that takes the prefix string to the state we just created, like that. Right, string to state. You can see here we're reading things out as U64s, casting them into state pointers, so it makes sense for here to take a state pointer, cast it to a U64, and store it. That kind of checks out. Again, here doing the same thing to read from it. So yes, I think that's what is missing. What? weird. Oh. Not sure why key and Dow would both be 0. Those should be other things. I mean, it doesn't make a lot of sense. Union ops first chars ops. The first thing is dot dot size 2. The second thing is what? Wait a minute. Blank size 0. Thought I checked this earlier. One of the previous streams that this wouldn't be a problem. There shouldn't be an empty right there. Ops with dot is wrong. Thought it was going to remove the string that was empty. Copy the set, remove all of those, so the only things left are the 3 that start with dot. And now it looks like dot dot dot, dot, and dot star. Good. Now string skip 1 character on each string. If that is greater than or equal to, lame, 1541. Okay. Hey, it ran to completion without crashing. Alright, so that's it. That's episodes, what was that, 7 and 8? Thank you for checking these out if you've been watching them. There'll be more to come. There's a lot to do on this project, and on 4coder in general, although I'm not going to be streaming the rest of that. But yeah, so we're kind of getting past the hill on, we're kind of getting over the hump on this transition optimization part. So this has been a little bit more involved than I expected, but yeah, I think we're going to not do this. But yeah, we're getting pretty close to being able to do this fully correctly, I think. The reason we've been doing all this weird set stuff recently is because we're trying to basically take the idea that there are these states that have transitions on them, remember? If you don't remember, I'll review for you. There's these states with transitions on them, and each transition identifies a set of things for which, like, those states, states combining the state of the flags in the state machine as well as the input from the character from the input, right? The combination of those things, if they satisfy the condition on that case handler thing, like if the case is condition, then it uses that case to determine what to do next, which state to transition to, what actions to take. Now the thing is most of those case conditions are specified as sets of possible conditions that would satisfy them. You know, any of these characters and no matter what flags there are, and any of these characters as long as this flag is set to 1, or any of these characters as long as this flag is set to 0. Those are basically the ways you can specify the condition under which a particular case should trigger. And because of that, they need to be represented as sets somehow internally to keep track of what cases can trigger them. But furthermore, when I say, hey, what I'm trying to do is I'm trying to optimize the idea that, hey, a particular case handler might not consume the input that triggers it. It might say, I'm only peeking at that input, and I'm transitioning to some other state that will actually do the consume operation. Well, that's really the almost necessary way to write the system when you're writing everything out by hand. It just makes it possible to sort of create clusters that are like, do all this work, and if you see something that isn't on topic, then go back to the root and it will determine what the new character we saw determines. Like, if you're going along parsing an identifier and you see an open parenthesis, you don't want to have the identifier parsing code understand how to transition to operator parsing. You don't want the number parsing code to understand how to transition to operator parsing. You don't want the thing that's detecting white space to know how to transition to numbers and operators and identifiers, and you don't want any of them to know how to transition to white space, and you don't want the thing that knows how to do comments, like I guess comments always have delimiters, so that's not a real case, but you get the idea. There's a lot of cases where you're writing the code that controls how to figure out, finish how to do a particular type of token parse, and at any point, if that thing sees something outside of the set of characters that continues that type of token, that makes it longer, it wants to just say, hey, I don't need to know what all that logic is. That logic is encoded somewhere else. Refer to that logic. So when you're writing it out by hand, that's what you do. You say, I didn't consume this character. I just saw something that was off, like that would end my series, and so I'm letting the root handler figure out what that character means for the, the token. But when you're optimizing the state machine, there's no reason for that to actually be the case. Yes, the information doesn't want to be duplicated in the stuff that I hand maintain, but I might as well pull that information in as close as possible to the point where it can operate right away, rather than having several extra steps through the state machine to figure out where to find actual information about what we're trying to do. So the idea is, if you say I'm peaking, all you have to do is say, well, look at the state you're in, right? Look at the thing you just read, the character you just read, and the state of the flags, and using that information, you should be able to look ahead and look at the state that you would transition to and just say, what would they do if they had read this character? Don't force them to be the one to read the character and to do the actual work. You just do the work that they would do, and if they would have done a peek as well, then you just take a look at where they would have gone, and you just keep doing that. Now, if you eventually find out that this process leads you back to yourself, you've just discovered a loop of peaks, which is a problem in the actual model anyway, so this is a form of type checking maybe. But on top of that, this lets us pull actions up towards the point where we first see a character and handle it there immediately, which is a really nice thing to have, so that we can cut down on that extra time that's spent looking ahead. It also will mean that certain qualities of the state machine will be easier to understand and easier to predict. Like, there will never be a situation where you put something into the state machine and it needs to report to you that it didn't finish what it was doing or anything like that. It'll always consume a character. It'll always consume one character, no more, no less, and it'll always emit everything that it can from that character and store in its state anything it needs to buffer without you having to do any of the work as the caller to do any of that. That's kind of an important aspect of how it needs to work, I think. So I think that it has more than just optimization payoff, but even if not, it's still a nice thing to have optimized out as well. To do that, we need more than just the ability to say, here's the set of conditions under which this case is handled. We also need to be able to say, okay, since I am not at runtime, I don't know the particular case that am in. I don't know the full state. I just know the set of states that can trigger me. And so when I go and peek into the destination state to see what it would have done, I need to be able to say, hey, what would you have done with all of these states? And so that actually means I need to be able to say, given this set of states that I am triggered by, is that, what case handlers do you have that are relevant? And then I'm pulling each one of those forward and splitting my case handler up into separate case handlers for each of those cases, right? So, yeah, that's why we have to do all this work. Just to recap for people who maybe either forgot where this started or who haven't watched the whole thing and are trying to enjoy it from this point on. But this is all in the name of optimizing the most sort of one of the two slowest parts of how this would come out if we didn't do any optimizations, is that figuring this part out. The other thing is we want to figure out how to isolate this into small lookup tables if possible. But that's a separate problem for another time. We're going to probably just do this and then skip to generating first, and then I'll have on my to-do list, what do I do if I want to optimize, do lookup table acceleration. And I should also throw in here type checking information, so I need to type check the delim match. Come on, delim match delim. Where is that thing? I guess I don't have. Yeah, I guess I don't have this without the prefix. Having said all that, it may not be possible to eliminate peaks in all locations anyway, in which case it might make more sense to say that what we're actually doing here is looking ahead 1 or 2 stages, and if we have to look farther than that, we would just stop. But I don't know. We'll keep working on it a little bit and see what we can actually achieve. But I just remember that delim match might not actually let me do this without peaks perfectly, because there's no way to know if something's gonna match a delim match or not until you go start doing the delim match. I guess I could pull the entire delim match logic up. It'd just be crazy. Anyway, there's that. And I also need to potentially trying to think. I thought there was a third thing I wanted to type check at some point. Anyway, there we go. That's a little more progress. Thanks for checking this out, and I will make more videos moving forward on this. See ya.